page 8 of discrete random variables. Suppose that x is a binomial random variable with parameters n and p. So x is distributed in a binomial distribution with n and p. The mean of x is n times p. Okay, we knew that. Now, what about standard deviation and variance? Do we know something about that? So for variance, which is sigma squared, the equation is very similar. The formula is very similar. You just multiply an extra 1 minus p times that. And so, of course, remember that the standard deviation is the square root of variance. So we just take the square root of sigma squared, which is equal to the square root of np times 1 minus p. Okay. np, np times 1 minus p, square root. Number 1, suppose that x is distributed binomially with n equals 6 and p is p. For each of the following cases, find the mean and standard deviation of the distribution. Graph the distribution using a column graph and comment on the shape of the distribution. Okay, so basically what we want to do is we want to use bin PDF, and we're going to have n is equal to 6, and we're going to have p equals 0.5 in the first case, and we want to find first the mean and the standard deviation for this. That's pretty easy, right? The mean we just saw above is equal to np, so that's equal to 6 times 0.5, so the mean in this case would be 3. And the standard deviation would be the square root of np1 minus p. So we would put square root of 6 times 0.5 times 1 minus 0.5, which is also 0.5. So that would be square root of 6 times 0.5 squared. We can do that with the calculator. Square root of 6 times 0.5 squared, which is 1.22. Next part, graph the distribution using a column graph and then comment on the shape of the distribution. So we could use the table to generate the data for this column graph. Similar to last page, we could put a function which will generate all the probabilities for each one of the possible x values. Now, remember how we always draw pictures for our binomial distributions? In this particular case, our binomial distribution has an n equals 6, so it would range from 0 to 6 in value, right? And then each one of these probabilities can be generated by doing bin PDF, right? So we already have bin PDF typed here, and in this case we already know that our number of trials is 6, and we know that our in this case our p-value is 0.5, so we put 0.5. And then first what we're going to do, we want to generate all these values from 0 to 6. So instead of putting 0 here, we're going to put x. And then we're just going to look at the table. And the table is going to give us all the values from 0 to 6 all at once. So if I want to graph this, I would like to see what the relative values are. It looks like the highest value is 0.31. So maybe I will do my y values as 0, 0.1, 0.2, and 0.3, because it doesn't really go higher than that. And then the x values would be centered here. I would have 0, I would have 1, I would have 2, 3, 4, 5, and 6. It says to make a column graph. So a column graph is not exactly a histogram because the columns won't touch each other. So this is my probability, the probability of x. And here are my x values. So I would have my first value being 0.015 about. 0.15 is super small, right? It's like you can't even see it. The value for 1 is 0.09. 0.09 is almost 0.1. So it would be almost to 0.1. 2, the value is 0.23. So that would be slightly above 0.2. And then the next one is 0.31. So that one goes slightly above 0.31. And for 4, it would be 0.23 again. And then the next one will be 0.09. And you can see that it's like symmetrical. And 6 would be 0.015 again. Okay? So they say comment on the shape of the distribution. Well, it's symmetrical. Okay, next one we're going to do the same thing, except we're going to do p equals 0.2. So we'll do that here. And in this case, first we're going to figure out the mean, which is NP. It's going to be 6 times 0.2, which is 1.2. By the way, you can tell by this distribution that the mean is going to be 3, right? Because you can see from the symmetric distribution that the center of mass of this distribution is 3. Okay, so if the center of mass of the distribution is 1.2, we're going to expect that the thing to be like more lumped toward 1.2, like that. The sigma value is going to be square root of NP times 1 minus P. And so for 0.2, it would be square root of 6 times 0.2 times 1 minus 0.2, which is 0.8. So that would be 6 times 0.2 times 0.8 square root. Square root 6 times 0.2 times 0.8. 0.979, 9 is rounded up to the next number, so it would be 0.98. And let's do the graph. So we'll put y equals binomial PDF, and instead of 0.5, my probability is now 0.2. And so now my table has, let's see, the highest value is 0.39, so we could do a similar scale to what we had before. Our highest value is going to be around 0.4. Let's see. And then we'll have values 0, 1, 2, 3, 4, 5, and 6. So our value for 0 is 0.26, pretty large. About halfway between 0.2 and 0.3. Next value is 0.39. It's almost 0.4. And the next value is 0.245. It would be halfway between 0.2 and 0.3. And then 0.3, for x equals 3, it would be 0.081. So it would be almost to 0.1. And then 4 would be 0.015, super small. 5 and 6, super small. Okay, so it's as we predicted. It's like, more to the left. And it says to describe, comment on the shape. Do you remember how we use the skewed positively or skewed negatively? So basically, if the bump extends to the right, we would say skewed positively. Okay. So that was for 0.2. The last one is going to be 0.8. 0.8. So for 0.8, the mu value is going to be 6 times 0.8, which would be 4.8. And then the sigma value would be 6 times 0.8 times 1 minus 0.8, which was 0.2. And look, the sigma value is going to be the same as this one, right? They're both the same because the p-value is just kind of the complement. So probably the shape of this is going to be like the previous one, except inverted or something, right? Because like instead of being centered around 1.2, like this is, it would be centered around 4.8, right? So let's do that. So what we're going to do is we're going to change our y equals. So our binomial PDF now has 0.8 instead. And then we're going to do the table. And so now 0 and 1 values are super small. And 2 is also pretty small. And the 3 value is 0.081. It's like almost to the first line. Then 0.25 about. And then 0.39. And then 0.26. So it's kind of the mirror image of this one, right? So this one would be skewed negative because there's the bump and then it extends to the left. Skewed negative. And then we could also say that it's the mirror image, or we could say it's the reflection of the p equals 0.2 curve about the center, which would be x equals 3. Okay? All right, last one. Bolts produced by a machine vary in quality. The probability that a given bolt is defective is 0.04. Random samples of 30 bolts are taken from the week's production. If x is the number of defective bolts in a sample, find the mean and standard deviation of the distribution. So remember, the mean is NP, and the sigma is square root of n times p times 1 minus p. And in this case, our n value is 30. And probability, I think, is 0.04. Let's see if they want to know defects or... Okay, yeah, they want to know defects. So our success, quote-unquote successes, are defective bolts. So there's a 0.04 chance of having a defective bolt. So out of 30 samples, we're expecting to see, I think, 1.2 bolts, because 30 times 0.04 is 1.2. What would be the standard deviation? The standard deviation would be the square root of 30 times 0.04 times 1 minus 0.04, which is 0.96. So that would be 30, let's do the square root, 30 times 0.04 times 1 minus 0.04, which is 0.96, 1.07. Okay. So we already did that. If y is the number of non-defective bolts in the sample, find the mean and standard deviation of the y distribution. So still n equals 30. But in this case, instead of looking for a successful result of a defective bolt, we're looking at the successful result of a non-defective bolt, which would be p equals 1 minus 0.04, which would be 0.96, right? So for this case, our mu is going to be 30 times 0.96. What is the mean of mean number of bolts that are not defective? So that would be 30 times 0.96, and that would be 28.8. Makes sense that these two add up to 30, right? And then last of all, the standard deviation is going to be 30 times 0.96 times 1 minus 0.96, which would be 0.04. Look, it's the same. We'll get 1.07 for both. Okay? So basically, the first distribution is going to, it's going to look kind of like this one, where everything's clumped to the left, and the second distribution is going to look like this one, and they're going to be like mirror images of each other. So this one's like a lump that's on the left side, and this one's going to be a lump on the right side. This one's kind of centered around 1, and this one's kind of centered around 29. Okay? And that's it.